Okay. Okay. It's my pleasure to give you this lecture. So first I talk nonstop today. So before you forget your question, please write down. Please write down your questions in a chat message. So after I finish this lecture, I go down a chat message one by one and try to answer all of those. Yes. Okay. The title is, as you can see, so this is a lecture it's given by UNISEC Japan. These are the co-authors. Yes, Dr. Tsuruda, Dr. Furumoto, Dr. Miyata, and Dr. Kitada, and Dr. Kuwahara from various organizations of UNISEC. So first are the introductions. So why we are doing this one? Okay. So in 2020, year 2020, so this very start of a pandemic, basically everybody was grounded. So all Japanese university professors usually go around and give lectures and very busy and doing travels and doing many things. However, in a COVID, in a pandemic, we could go nowhere, no travels, okay, no lectures, and staying homes. And well, it's a good time to do research. However, we found, we discussed, is there anything to do, something meaningful or to spend this time? Yes. So we decided to have these remote sessions on lessons learned from a university satellite project in the UNISEC Japan. So we started in June or July of 2020, and did almost 6 months. Yes. So in these sessions, everybody talked very honestly what really went wrong, and what kind of lessons we learned, and how we implemented those lessons to the later project. So it was quite nice sessions. And these activities, JAXA learned this activity, and they JAXA liked this one. So they offered some help. And basically they provided UNICEF funding to do survey on the lessons learned of mission assurance. So we wrote a report, a massive report of 439 pages. Unfortunately, it is Japanese only. And in this report, we did analysis about success and failure cases and their causes. And we extracted a requirement for the mission assurance. So following this activity in 2020, in 2021, we further worked on this mission assurance handbook for university-based lean satellites. So basically, we did further analysis of the failure causes, and we also worked more on this requirement for the mission assurance. So we did a very deep, we did interviews with professors. I think each interview lasted 3 hours or something. Yeah, so we did a very deep interview and tried to extract and what really went on and what were the root causes. Yes. And based on those activities, we published this mission assurance handbook for the university built lean satellite. And this time we made both Japanese and English version. Yes. So that's how the book was made. So from now on, I'll first explain, I'll show you some examples of lessons learned and root causes. And after that, once I'll talk about the contents of a mission assurance handbook. Okay, I'll show you the 7 or 8 the examples. So first examples, it is a 3U CubeSat. Okay, and the satellite was very difficult to assemble. And every time the satellite was assembled for testing, it suppressed the schedule significantly, but because satellite could not be assembled in one day. It took 2 or 3 days every time. And also, during the safety review, the team promised JAXA will do 3D measurement each time the satellite is assembled. Because they promised every time after spending so much time in assembly, they have to bring the satellite to some special facility where they can do the 3D measurement. And because of that one, software development progress was far behind the hardware development. And eventually, due to a collision of I2C, the satellite entered some infinite loop. And luckily, satellite recovered after, I think, 2 years. Yes. Because of complete power shutdown. Yes. But for the first 2 years, yes, satellite was really dead. Yeah. Although it recovered. And well, obviously they promised more than enough for the safety requirement verifications. Well, perhaps they wanted to prove that they can do something, but to my opinion, they didn't have to. Yes, they just promised too much. And also, when they decided mission definition, when they defined the mission, only faculty members was involved. And so students were not involved in the mission definition. So the kind of motivation was kind of not so high. And this was their first satellite project. So they had no experience. So satellite structure was too complicated. So they didn't realize that the time to spend in satellite assemblies is so long. And also poor schedule management. And so long-term end-to-end test was not done. Because of that, they couldn't detect those I2C collision. Another one's 1U CubeSat. Well, this was a really bad case because this ended up in a dead-on arrival. Satellite was released into the orbit, but no signal, even a beacon signal, was heard. Well, it is 1U CubeSat, so it has many single point of failures in a satellite design. And one possible reason is power systems. In the second satellite, they found that they connected their solar cells in the wrong way. And they believe that they did the same way in first satellite. And first it was a reason. And they mistook a bypass diode tab as an electrode. This is the solar cells. And this solar cell is made by Azure Corporation. Actually, at the QTech, we also use. And this is very, confusing because we have this tab. And they thought that this is kind of an electrode. So this is one electrode. Therefore, this is another electrode. And that was a mistake. This is a bypass diode. So it's not. And also, the delivery date was fixed. And so the satellite had to be delivered regardless its condition. So they had very short time to do the system test. So they basically they didn't know what to do to build a satellite. And also, this is more important, didn't know who to ask and where to ask questions if they had any questions. And because they could ask others, but even they didn't know where they should ask. And 2U CubeSat, this is another example, 2U CubeSat. In this case, communications was very insufficient. So they couldn't establish a good communication because the ground station preparation was very insufficient. And they didn't check the ground stations works or not using other satellite. And basically, the team was from the mechanical engineering department. those students had a little knowledge of communications because in the mechanical engineering department, we teach structures, we teach thermodynamics, fluid dynamics, but no communication. And so they depended on external supporters regarding the communication systems. And but it was very difficult for mechanical engineering students to point out any problems, even if they find some things in a system test, because they couldn't know how to address those questions regarding communications. So it was very difficult to communicate. Yes. Whether those who joined later, you can ask question anytime, writing on a chat message. So I'll answer one by one. So I'll go through. I have about 60 pages. So it may be it's very easy to forget what questions you have. Okay. So I encourage you to write a question. Okay. So the root cause was they depended on an amateur radio expert outside the campus for the radio. Well, usually those amateur radio experts, they are very good. They are almost professionals. And because they always hands-on, so they have also very good hand skills. However, there are some physical distance between those amateur radio people and universities. So communications between the expert and the student was very difficult. And also the principal faculty couldn't take care of those gaps properly because the professor also himself was from the mechanical engineering. So the root cause is really lack of necessary expertise, in this case communication, for the satellite project. Another case, this is not a CubeSat. This is kind of very big, the lean satellite, 50 kilograms Earth observation satellite. This case, power budget didn't have enough margins. So because of power shortage, frequent satellite reset occurred. So satellite resetted many times because the power was low. So every time the reset occurred, the attitude control history was overwritten, and the complex attitude control had to be restarted once again. Actually, we are having the same problems recently with our satellite. Yes. So yeah. So it's very important to keep the attitude control parameters after this. Yes. But anyway, it took too much time to establish the proper attitude for the missions because it's Earth observation, so they need to point the camera. Also, they need to point the antenna to downlink the image. That they couldn't. But they eventually succeeded in three-axis stabilizations and pointing, but it was too late. By that time, one of the reaction failed, and so that's it. And so because of insufficient attitude controls, no image data could be downlinked. So mission couldn't be done. So it was the first satellite for the team, and lack of experience in satellite system design and development and operations. So again, there is no time to do full system test to check the power budget under flight representative conditions. So they couldn't do test as you fly. So basically, we have to test as we fly. This is another example, 50 kilograms microsatellite, the Earth observation microsatellite. In this case, again, power system, the battery charging was not designed to stop chargings after full chargings, or usually should. Yes, yes. Otherwise, you may damage the battery. So usually the battery charging should stop. So they needed to have a very delicate charging maneuvers in orbit. Also, they had no knowledge of a bypass diode or Volkin diode in solar cell circuit. usually you need a bypass diode. Then even if one cell is covered by shadow, the current from solar cell can flow this bypass diode. Otherwise, if it is in a dark condition, solar cell acts as the diode in opposite direction. So the reverse voltage is applied to the solar cells, and it's very easy to break those triple junction type solar cells. Those are gallium arsenide cells type solar cells. So that's why in this case we have bypass diode for each individual solar cells. Right? For most of the CubeSat, you don't need, because there are no way you get some shadow on a solar cell. But in this case, in this satellite, it has some the deployment mechanism. So there are some possibility that some shadow covers some part of the solar panels. Also, we need a blocking diode. If we don't have this blocking diode, if this string is damaged, if we don't have this blocking diode, if these strings generate power, the current may flow this way, because this is a diode in this direction. So to isolate the damage of this string from others, usually we need this blocking diode. So they didn't know. So a shadow on the solar panel occurred, and it killed the entire solar array circuit on 50 centimeter panels. That's very significant. I think that satellite had only four panels pass. Yes, 4 panels of the solar panel. So it means they lost 25% power. And when the voltage became low, the satellite computer entered zombie state. That means it cannot function or it cannot reboot completely. So the root cause was, yes, again, it was a very fast satellite for the teams. So it was a lot of experience to check the design made by the power system vendors. So this battery charging system, they outsourced to the outside vendors, and they just trusted too much. And also lack of experience of doing system test, and by doing system test, and probably they could find this kind of issues. Okay, this is the 7 kilogram education tech demo satellite. Actually, this is one of our satellite, QTech satellite. Yes. This is Hollywood. This is our first satellite. The satellite deployment was very successful, and housekeeping data was collected for initial three weeks from the deployment before doing the missions. So because this was the first satellite, everything was new. So we are so happy. And we are just checking satellite housekeeping data every day. And I still remember that after 3 weeks, the students started saying that perhaps we should start a submission. And so I said, yes, okay, yeah, let's do. And I left to Europe for the conference. So I was thinking to take some rest in Europe. However, I got an email from Japan that they lost the communication suddenly. And it was due to the single event latch up. We know everybody blames radiation first if the satellite doesn't go well. But we had a hard evidence of the single event latch up. This is the data we took in orbit. This is the data when we recovered from a single event latch up. And even during the single event latch up and the satellite hung up, it could collect the housekeeping data. So it was collecting housekeeping data, and current consumption very high. And after power reset happened because the battery became empty. And then we had this the new state. This is nominal state. So we had about 150 milliampere jump due to the single event latch up. And yes, so satellite recovered, but we had a very frequent failure, and it disrupted operation. So we usually have overcurrent protections to exit from the latch up. Yes, this satellite also had this OCP, but it didn't work because we set the threshold to the 500 milliampere. So, but actual latch up current was 200 milliampere. So we should have set the threshold 150 milliampere plus. And once the current jumped more than 150 milliampere, the circuit breaker should have automatically shut off the current and restart the satellite again. But because the threshold value was set to 500 milliampere, it couldn't. So the code was very clear. So the root cause was that we decided OCP threshold value without any basis. So I asked the student why we chose 500 milliamperes. And he said he consulted with some expert from JAXA, and expert said, maybe 500 milliamperes is good. The student thought of, because expert says so, I think he trusted, and I didn't have I had no capability of checking that the 500 milliampere. So we trusted. And so we put this cell protection functions. However, it was not verified. So we thought maybe it would work. And more important, we shouldn't have waited 3 weeks. We should have done the main mission much earlier. So in 1 week or so. So many satellite fails very early. So we should do the main missions as soon as possible. Okay, this is a constellation of 51U CubeSat. Again, this is a QTech satellite. This is you can see from this satellite, it clearly shows the name of satellite. This is BUZZ 1. We have a 51U CubeSat. So we carried this experimental patch antenna for both UHF and VHF. And the gain of this patch antenna was not as good as expected. We were told by the person who designed this patch antenna, so gain was enough. But the real gain of some of the flight models was not good. So we couldn't do the uplink. CW beacons we could hear. It was very weak. Because we couldn't do the uplink, we couldn't get the FM packet. And this problem was not detected by the ground test because the flight model antenna arrived at the very last minute. And no system communication test was not done using the flight model. So the root cause is that satellite design, this demonstration of new technology such as patch antenna was very inconsistent with the satellite mission. Satellite mission was education. Yes. And also we had a lack of experience in communications. So we couldn't understand the risk of a patch antenna. So also we should have considered this advantage of constellations more. We should have selected a strategy of making at least one satellite survive, rather than making all the satellites survive. So I chose a strategy of making all satellites survive, but I was wrong. So I should have chosen the making at least one satellite survive. So that kind of decision, use patch antenna was made only by the principal faculty. So no other member could challenge that decision. So yes, that was a really management issue. This is another example. This is a constellation of 3 1U CubeSat. This is BUZZ 2. Yes, based on the BUZZ 1 lessons, yes, we abandoned the patch antenna, normal patch antenna, especially on UHF, VHF. So we put those deployable antenna, and thanks to that one, yes, downlink was quite strong, Yes, CW econ is quite strong. However, it took 1 year to have the successful uplink. We found that there are very strong internal noise inside from the power board. This problem was not detected during ground test because we use a reference dipole antenna in a test, and we didn't know that the reference dipole antenna had an internal attenuator of 10 dB. And so it was overlooked, and that resulted in overestimation of 10 dB in a link budget. So we overestimated the link budget. So the root cause was, few expertise in communications. We couldn't check the test setup consistently. We had one student who was very good at communications. We just relied on that student. So others couldn't check what he was doing. Also, we had a lack of knowledge that the internal noise affect uplink signal reception. So it is very important for the 1U CubeSat because the signal coupling, noise coupling is very significant because the bodies are so small. And so this means when we calculate the link budget, the background noise in the link budget was chosen without any basis. We just assumed some noise temperatures and calculate based on U over EB over energy per bit over the noise. So I think that is wrong. Yes. So this background noise we really need to measure. Not that yet. We need to measure signal to noise ratio, which we can communicate with the satellite. Yes. That will be in a mission assurance handbook. So these are the lessons we have learned and we have seen. There are many more things. Yes. If you can read the Japanese, you can go through those Japanese reports. Yes. And so what we see, these common root causes is that first, poor schedule management. You see, many satellites had little time to do system test. And insufficient team talent and skills, inconsistency in requirements, improper verifications, plannings, a wrong strategy to avoid total satellite loss, and insufficient full system end-to-end test, and difficulty in assembly, integration, and testing, and poor understandings of the rationale behind the design. So there are many common things we can find. So based on those, and we wrote this mission assurance handbook. So what is a mission assurance? Mission assurance is a series of activities to identify the factors in design making operations, those things that will jeopardize mission success. And we have to eliminate those or decrease effect of such factors. Those are the mission assurance. So basically, we try to improve mission success rate. And the university satellite is categorized as lean satellite. I use the word of lean satellite from the beginnings, but to explain what a lean satellite is, it is a satellite that uses non-traditional risk-taking development and management approach with the aim to provide satellite value to customers or the stakeholders at low cost and with short time to realize satellite mission. So if you want to know more, you can check this one. Yes. And this lean satellite tolerates risk, yes. And so it starts from it tolerates risk, but we still need to achieve the mission success as much as possible. So it's not a failure, it's not option. This strategy taken in a very big satellite, but we are not saying failure is accepted. Yes, well, we accept a failure of a single satellite. And if we fail, we fail. We should fail early. But we have to learn the lessons and also to fail early. Yes, we sometimes accept the tolerate risk. So So this handbook targets satellite project at universities and polytech college in Japan. So it's not only for the first project of the university, but also the second and the later project. Yes. And we write summary of points to be kept in mind of faculty members, especially faculty members, yes. And also students to improve the mission success rate. And it's organized in order of project life cycles, and it is free and published and available online. And many of the content is still applicable to satellite project in UNISEC company, also non-Japanese organizations. That's why we have this lecture today. So the purpose of today's lecture is to introduce this mission assurance handbook and correct your feedback. So we have the Google Forms for your feedback, and I'll show you the link later. So after this lecture, after hearing what I say today, if you disagree, yes, please write that, yes, I disagree, and we should write this way. Or if you feel something more should be added, you can write. And so anything is fine. So please give us your feedback. Yes. So that's how we want to revise this one. Yes. So we want to correct those the experience or the wisdom from all over the world and try to make this handbook better. So you can download handbook. Yes. Use your smartphone and capture the QR code below. Yes. And if you miss the last page, yes, you can still take this. Yes. And okay, introductions, project management, mission definitions, and conceptual design, and the detailed design, and production, testings, operations, and post-operations. From number 3 to number 9 are in order according to the project life cycles. Yes, and the sustainability of university satellite programs. That's at the end. So I'll go through some of the important sections, which I think. So yes. So first, project management, schedule management. So we saw that many project fails because of insufficient project schedule management. And so very little time spent in a system test. So I thought it was good if we can have some guideline for the project milestones until satellite delivery. So let's say D is the time we deliver satellite. Then 6 months before, maybe you should finish EM testings and confirm that the satellite functions as a system. So in 6 months, you procure FM hardware and start do the FM hardware, the assembly integrations. So using 3 months, 2 months for testing, 1 month for software testing. And before CDRs, maybe 7 months. The 6 months is for FM, 7 months for the EM, because in FM, in the EM stage, you run something. So it's a learning curve. So you can do more efficiently in the FM stage. But anyway, in D-30 months, you finish proof of concept. So confirm that the missions are feasible technically. And finish EM design and start procurement. And the hardware procurement takes some time. Do not assume that if you order today, things will come tomorrow. No, no way. If you order today, things will come 1 month later. Then you're lucky. Yeah. So hardware does not come next day. So it's about 13 months after PDR. Yes. And before PDR, for the proof of concept, it depends on what kind of mission you do. Yes. And project teams. So it's not possible to have all the talent necessary for the project by students alone. Yes. after all, students are beginners. And even if they are distributed among different departments, always you have some skills, some talents lacking. So you need to find a solution to fill the shortage. First, procure. So buy, outsource with money. Yes. 2, collaborate with external people. And 3, expect students to grow. Well, that's another way. Yes. However, it's risky. Yes. Even for 1 or 2, the requirement for the procurement or outsourcing must be made by the team. Otherwise, once they are delivered, you can't really verify whether it fits to your system requirement. And it's important to keep persons familiar with the satellite design for operations. So because in many university projects, students graduate. So it's better to finish or need to finish project from kickoff to operations in 3 years. In Japanese university, 3 years is a very typical year for a student, engineering student to stay in a laboratory from senior year of undergraduate and 2 years in a master courses, so 3 years. And role of principal investigator, that is a professor. He or she is responsible for keeping the student motivation and responsible for securing the communication channels for the external assistance. That's you remember that I talked at some satellite project had no way, didn't know where to ask and what to ask. And well, at least professor should tell students, ask Professor B over the University A. And okay, I'll make a first contact. And then after that, you send the email. Something like that. Yes. Otherwise, students are very shy, or at least in Japan. Yes. So very too shy to send an email to very big professors. So professor should do at least for the initial contact. So for the safety requirement, yes. Yes, if you don't comply with the safety requirement, it may lead to very serious delay of the schedules. And in the worst case, the satellite is not launched, dummy mass will go instead of the satellite. This really happened. So this is a picture. Actually, this is a folio for our satellite. This is 2 other piggyback satellites. This is supposed to be a bunch of CubeSat. But they couldn't fly because they couldn't meet their safety requirement. So instead of those satellites, they put a dummy mass. So it is a very nice picture to scare everybody that if you don't follow the safety, your satellite doesn't go. So at the end of conceptual design and detailed design, list up issues related to safety requirement and confirm that with the launch providers. Yes. But if you ask some expert, some external review, those who made a satellite, 2 or 3 satellites before, they can easily pinpoint what would become the problem. So I think it's very good if you can ask external review at this moment. Yes. And the team needs to agree with launch provider on safety verifications method that can be done with a minimum effort. The safety verification is necessary, but non-value adding activities. Do more value adding activities such as mission assurance. So this is a lean philosophy. We can categorize activities into the 3 types. You can also think of your daily life. Okay, I'm talking to students. Okay. So 1, value added activity, improve satellite reliabilities or improve attitude accuracies or the others. So such as for your case, maybe improving your academic grade. Okay. Another one, non-value added but necessary activities, such as safety review and a radio license and space activity law in case of Japan and others. For your daily life, first you should eat and you have to take a shower and you have to sleep, those things. And third one is ways, complete ways, such as looking for tools or others. Yes, or daily life, I don't know. It depends on persons. So key point is eliminate waste and make the non-value added but necessary activities efficiently, or transform that non-value added activities to value added activities. That's a lean philosophy. Yes. So in the mission definition phase, the feasibility is important. You should know the limit when you define the missions. Limit of the team talent and skills and the budget. And students should realize that the professor is not a god. He or she doesn't know everything to judge the mission feasibilities. Professor is very good at pretending that he knows everything. He or she knows everything, but it's not. Yes, the professor doesn't know everything. So don't rely on the professor too much. So also professor should be open-minded to suggestions, comment, assistance by others. That's important. And so let's say 3-axis stabilization from the first satellite. First, it won't work. So it's better avoided. High-speed communication by mechanical student were too challenging, not good. Yes, something like that. And mission success criteria is also important. This is becomes the kind of the key index, key factors of your satellite activities. So minimum success is things to be achieved even if the satellite has problems. Okay. Many educational satellite, not recently, but before 10 years ago, many university satellite projects says, well, minimum success is finish the satellite. I don't think so. At least satellite needs to be operated. Yes. So yes, something like that. The full success things to be achieved when the satellite works as expected. Yes. And extra success is something more than expected in addition to the full success. So use quantitative indicators such as how many pictures you download and how much communication speed you achieve and those things. How many kilobytes, how many megabytes of data mission data you download or something like that. So you may need to change those criteria as the project goes on. However, always examine whether the meaning of the entire project can be achieved, such as can we satisfy the project stakeholders? I mean, sponsor. Yes. So when you discuss a design change, you need always to examine whether the minimum success criteria can be achieved. So try to achieve the minimum success criteria as soon as the satellite is deployed into orbit. So in that sense, yes, teams should be aware of this minimum success always. Yes. So in the conceptual design phase, the requirement management. So check consistency between the mission requirement and the design requirement. So design should satisfy the mission requirement. No design requirement that doesn't fit to the mission requirement. So one example is this one. No experimental patch, no experimental things in an education satellite. And external review by experienced expert is very effective. So this expert can pinpoint that there is something wrong in this requirement, but doesn't fit each other. So teams, especially principal investigator, need to be open-minded to such an external suggestion. And the verification plans, yes, we need to make what the test we do at the very early stage of a satellite project. And so you shouldn't use the design that cannot be verified. Yes. Also, verification plan must be doable. So this is a list of minimum tests or ISS release CubeSat, electromagnetic compatibilities and those things. Yes, I'll come to this one later. And in the detailed design phase, you select parts and components. There are many options. So when you select a vendor, buy something from others, price and performance may not be the key factors. Is it easy and is it quick to procure, or is it easy to handle, or is the response to repair request, is it good? So those things are more variables than the size, price, and functions. So you can find many vendors, but be careful when you select the right one. So for a series of satellite projects, such as programs, so change of bus component specification should be minimized. You can ask vendors to make, for example, the radio. But you shouldn't change design unless you have very good reasons. Because even the tiny changes cost a lot of money and time. So we need to be aware of that. So also, when the components develop jointly with the vendors, after all, eventually those designs and know-how should be transferred to the vendor. Because university cannot keep those know-how, so it should be transferred to the company, and the company can keep supplying. So it's related to sustainable supply chain. But risk management, FTA, FMEA, try to minimize risk based on priorities. External review is effective. And we should be aware that FTA or FMEA, we don't teach in the school. Well, I teach at the QTech. I teach FTA, FMEA. So all of my students should be aware of this FTA, FMEA, but not in other schools. Yes. And so we should start from the levels students, professors can understand. And we list up a single point of error and prioritize risks. Yes. And we should also look at those works, such as long command and long assembly, those things. And we have to design satellites so that it can survive. So we need to avoid complete failure, such as loss of communication. So in Japan, so we use something called God PIC. So it's a microcontroller PIC 16877. That's for power reset, because it's proven that it's very strong against radiation. And we better confirm that battery can be recharged even if it becomes empty. And the satellite works without battery using solar panel only. And if we have enough volumes, we should put the redundant communication links. And power budget must be feasible. It must work even we lose attitude controls, even if we fail on solar panels deployment, and even if we lose one solar panel. So if you look at this one CubeSat, in this case, we have 5 solar panels. If by some reasons we lose 1 solar panel, this means 80% of power loss. 20% of power loss. So the power becomes 80%. That's significant decrease. So sometimes it becomes a single point of failure. So in this case, you have 5 single point of failure in parallel. It's very risky. So you need to set the power budget so that even if you lose 1 solar panel, the satellite can work and do the mission. Also, if you do the power reset, you have to verify satellite can recover from power reset. Sometimes, yes, it becomes zombie. Yes, it cannot shut down completely. It cannot reboot completely. That happens, yes. So you have to verify that, yes, it can. And also, when we discuss the design change, we have to evaluate the benefit and the risk. And for the discussion, it's better to use the minimum success and full success criteria. So this example, actually, this one we discussed in our project. So we had two radio. We had two antenna. But all of four were new. So to improve the success rate, we discussed, can we just make one switch here? But we can have the combination of radio A, antenna D, and radio A, antenna C, radio B, antenna C, radio B, antenna D. Then we can improve the success rate. However, we had also risk of this RF switch stuck in an intermediate position. In that case, no communication. So we divided radio A connected antenna C, radio B connected antenna D. So even if this one lost, if one channel survive, it's okay. And operations, it must be easy to operate. You have to image how to execute the missions. And stored command is very useful. I think many satellites use this one. And uplink command should be simple because small number of bytes is good to uplink. And the GS softwares can adapt remote and automatic operation. And yes, keep housekeeping data history before power reset. Also, yes, this one. Keep important parameters before and after reset, especially those control gain of attitude controls. Yes. Every time if you have to uplink, then when you lose attitude, that means communication is bad because antenna is looking at antenna may be looking at antenna may be looking at any direction. So you have a less chance of uplink. So if you have to uplink, those are the very delicate series of those numbers. It's very difficult. So you should keep those important parameters. And reduce the number of fasteners, harness, connectors as much as possible because every connectors, every bolt, they are also harness. They are possible cause of workmanship errors. And also implement the mitigation against mistake in the design. This is one example. This is a PCB used inside satellite. This is front side, where we should have this connector. This is back side. So we have this. We cut one part, one corner. This one, so that when we look at PCB, the cut the corner. If the corner cut is shown on the right, that means this is front. So that implement still makes mistakes. However, yeah, it's better than nothing. Okay, and save connectors. Every time you insert and remove connector, you accumulate damage to the connector. So frequent attach removal may damage. And also physically inhibit against antenna deployment. So you may want to work on the software until the last minute, but the deployment may not be allowed after the final safety review. So yes, preparing jig for the assembly test storage, and also think how to carry a satellite. Do not carry a satellite by hand, especially by one hand. Okay. Yes. Okay. This one, you need to carry by two hands. So in-house or outsourcing. So often student makes a mistake that the purpose of education satellite is to acquire hand skill. No, it's a practice systems engineering and project management. So we do not teach soldering in a satellite project. There are much more cheaper and easier opportunity to teach soldering rather than satellite project. Also, better not to try save money by making in-house. So after all, it may end up in a schedule delay and cost increase. So you can buy quality and time with money. Some students, yes, they are very good. They have very good hand skills, but some no. So relying on student hand skills is kind of risky. So in the productions, the compliance with safety requirement. So verification of safety requirement in FM stage is very critical to pass safety review. And how to control hazard must be agreed before FM assembly between the launcher and the satellite. That's very important in Japan. Yeah. And need to verify that control methods were implemented according to the agreement. So that we do at the final stage of safety review. So before moving to FM assembly, the team members, especially those who work on AIT, should be aware of what procedures they have to follow and what document they need to make. So for that one, good communications between safety officers and AIT team is important. Safety person says, I told you to measure. But the AIT team said, that's not what I was told. So this kind of, fight occurs very often. So please avoid this one. So in testing, EMC, as I said, this self-generated noise is important. So verify that communications link has enough margin. So especially uplink, yes. So this is not in FM stage. This should be verified in an EM stage, because if you find that in an EM stage, it leads to significant time delay, because you may have to replace some parts. And end-to-end mission test, so verify basic data flow of main missions, such as command uplink from a GS to the satellite, and the satellite do the missions and send the data to GS radio and check on the GS PC. If the mission is to take a picture, confirm that the PC can show the picture. So it's better to make a first very simple flow. So after that one, you can make the detail. Yes. System function test, move to FM assembly as soon as FM components are delivered, and start a function test as integrated systems. Do not wait all the components come together. You should start from the things things are available. So, and also check consistency of data sent from satellite. Don't assume that if the data is sent, from satellite, then it is okay. But you have to check the inside of data. And it's better not to move to environment test before you solve the problems, because you cannot isolate whether it was due to the environment or due to the functionality. And end-to-end long-term operations, and you find and fix bugs of flight software and operation rehearsals and the link budget confirmations. So this is the power amp in ground station. This is low noise amplifier in a satellite. So before coming to the satellite, we have this line loss, and we have this antenna gain, free space loss, antenna gain, and line loss. Okay, we have noise levels. Sensitivity must be higher than noise levels. This is the required SNRs. And received power must be bigger than this. But the problem is that these noise levels, measuring these noise levels alone is extremely difficult, almost impossible. So you have to measure this sensitivity. And by measuring sensitivities, you confirm that how much link margin you have. In deployment test, 25% of university satellite end up DOA. So is it due to antenna deployment failure? But perhaps if you see very weak beacon, if you hear very weak beacon, perhaps antenna was not deployed. But even if antenna is not deployed, usually beacon, most signals are the very high gain, a very, very high link margin. So even if antenna is not deployed, probably you can hear very weak mode signals. If it is completely dead on arrivals, if you hear nothing, most likely power systems or software. Yes. But anyway, you need to make sure antenna can be deployed in the worst case, yes, in a cold and low battery. Anyway, because even if you can hear the mode signals, very weak mode signals, if antenna is not deployed, no mission can be done. So, fit check. Yes, you may have experienced that the CubeSat may not doesn't fit to the port. If that happens at the satellite delivery, yes, it's really nightmare. And the best and simplest way is to do fit check with an official port. Official means the port you borrow from the launch provider. Yes, there's some kind of dummy port. You can make a port yourself, but these internal sidings are some, yes, the precision really matters. So it's better to do both for EM and FM. And thermal vacuums. Okay, thermal vacuum is a thermal vacuums. So whether you are testing 3-ton satellite or 1 kilogram satellite, it's same. Yes, thermal vacuum, thermal. The method of doing thermal vacuum is the same. And however, the temperature conditions, when you do the thermal vacuum, you have to define high temperature limit and low temperature limit. And we used the lot of thermal analysis to define that high and low temperature limit. And sometimes do even a thermal balance test to check those analysis. However, nowadays, there are many CubeSat already flown, almost 1,000. And so also many CubeSat are really same. They almost 80% or 100% are covered by solar cell cover glass. So you can use those flight data. So if you can find flight data of similar satellite, the size 1U or 2U or 3U, 6U, flown in the same orbit, sun synchronous or ISS, you can use that data. And it's more reliable than the thermal analysis. One important thing is for ISS, use high beta angle for high temperature because the temperature changes. Temperature is very high at high beta angle because you don't have eclipse. So evaluation of test result, something wrong happens, especially in a thermal vacuum. Something which you didn't observe in a laboratory, but once you start a thermal vacuum, you may see something occurs randomly. You have to record the observations and don't be optimistic. And you have to face to that phenomenon. So you have to fight against normalcy bias, such as perhaps it won't happen in orbit. It was just a random noise. We just saw illusions. Let's forget about it. So don't be optimistic. You have to face it. And also another thing is confirm that the test equipment is used properly, especially the RF equipment. Not many students have experience of the RF equipment, such as spectrum analyzers or the signal generators and antenna. So they use often wrongly. So read the manual carefully. Yes. And those test setup need to be checked by multiple persons. For operations, the good location for ground stations, yes, of course, no high buildings around site, no noise, and short distance between antenna and radio. But this number 4, number 5 are rather important. The radio room must be comfortable and also which is very near to the office and 24-hour access. Or usually satellite comes even in the midnight. Sun synchronous orbit, it may come 1:30 a.m. If you don't operate, you lose half of the satellite bus. Okay, and easy access to the antenna is also important. This is a picture when the antenna is broken after the after typhoon. And yes, this is on top of 8th floor roof of the buildings. I don't want to be here. That means I cannot send a student here. So I always ask professionals to come. So the one idea is to have some elevator type of antenna so that you can get this antenna go down, come down, and you can access this one by standing here. Also, when sometimes you may find that you cannot communicate with the satellite. In that case, yeah, it's better to check the antenna pointing. Yes, because the antenna is constantly receiving the wind, so it may orient a different orientation. In that case, do not use a compass to find the north because the magnetic north is different from geographic north. If you look at this antenna pattern of UHF Yankee antenna, if you misalign 10 degrees, it really matters. Yes, so slight misalignment really matters. So if you notice something wrong in the daily operation, you should check. And the operation phase, operation plans, obtain frequency license as soon as possible. This is the case for Japan. In Japan, we get only preliminary license before launch. And need full license to operate the satellite officially and publish the result. I once got a phone call from the Ministry of Communications that one of the students are listing postings a result on the SNS, and the Ministry of Communication directly called me that don't do that. Yes, and yes, I immediately told the student to take down everything from SNS. So that's the case in Japan. That may be different from in your country, but in Japan, yes, we have to. And do the main mission first. I explained the lessons learned from the Horyu-2. So many satellites, not ours, not only ours, but many satellites fail in first several weeks. But if you pass initial 1 month, there's a good chance that it can survive for a long time. However, in the first several weeks, especially first 1 week, yes, it's really a key. So get the license as soon as possible and do the mission. So don't be relaxed with the beacon signal. Well, things may not go well. We may have anomaly. So never give up. So professor should keep motivations of the teams so that they can work and keep the hope. Also, if something goes wrong, yes, we need to follow FTA. Yes, and that's important also for the next project because we have to reflect those lessons. And it's better to check along the information flow. This is the information flow diagram from ground stations to the antenna, radio receiver, communication computers, CNDH, mission payload, and OBCs, and radios, and antennas, and ground station PC. So if you hear nothing from the satellite, you examine each block and logically eliminate the possibility that something went wrong. So narrow down the candidate and do as much as possible. So you need some logical thinking for that. So after satellite operation, yes, lessons learned, documentations, and sharing know-how. That's important. Okay, sustainability of university-built satellite programs. So yes, you have a lot of you have a series of satellite projects, second satellite, third satellite, fourth satellite. You should build other programs. And in the program, yes, professor should be engaged as a program director. And also, sometimes junior researchers, such as postdocs, are involved. So we have to think of how junior researchers can build academic career from these programs, because it's kind of difficult to write a peer-reviewed journal paper from the satellite project. So that's a professor job to find an academic career. And also, the build and the strength, the base in universities. So support from the university management is important. And if you give something to university, you can get something from university. It's a give and take. Yes. Well, some professors do not like university management, so he or she does by himself. That's okay. But if you can work nicely with the university management, I think it's better. So also transition from a project of Professor A to a program of Professors A, B, C's, and more is important. Okay, fundings, efforts by individual professors is necessary. There are no miracle. I cannot tell you any secret. Sorry, I can tell you only this one. Money won't come from the heaven. So do something. Sorry. I wish I can say something about it. For the conclusion. So Mission Assurance Handbook for University-Based Lean Satellite was published in 2022, and summary of points to be kept in mind by faculty members and students to improve the mission success rate are written. So it's only 40 pages. And many of them apply to non-Japanese universities and new space company. And handbook is open to comments by the Lean Satellite community worldwide, and to be reviewed globally, and the comment will be reflected in the next revision. So please give us your feedback and check this QR code, and you can go to the Google home.